This is Mr. Pillar, ECET273, Modern Energy, lecture number 3. We're going to talk about what a power factor is and how we need to correct it and why we need to correct it. This is based on Chapter 2 of the Square 9 of DeWitt text and Chapter 11 of the Frodo Patrick text. We shall define a power factor and define the way to correct it. So power factor is the ratio of real power to apparent power. So that's P divided by S. That's also the definition of cosine theta. We express it in the decimal of a percentage. A decimal or a percentage. Capacitive loads have leading power factors. Inductive loads have lagging power factors. A unity power factor is perfect, and that's a totally resistive power factor. So like I said, a unity power factor of 1. Ideally, we're going to end up somewhere between 0.9 and 1, and we optimize for cost. So if you think about the triangle, the power triangle, you have S as a hypotenuse, P as the adjacent to the angle, and Q as the opposite from the angle. So we're talking about the ratio of the P to the S, which, like I said, is cosine theta. If we have a highly reactive load, we end up with a very large theta, which decreases the power factor. It becomes a factor of 0.8, 0.7, 0.6, all the way down. If we have a very small reactive load, a small Q, be it a positive 90 degrees or a negative 90 degrees, we have a reduced angle, which would reduce our power factor. It's the cosine theta. Cosine of 1 is 0. So angle 0 has a perfect unity power factor, which means S is completely equal to P. So P divided by S equals 1. Why don't we want an excessively reactive load? Well, an excessively reactive load means that you actually increase the current load, which means you have to increase the size of your wire, size of your transformers, and that's just the nature of more current, and you get less power. Using the beer mug here as an example, kVA is the total mug. That's what you pay the bartender for, or that's what you pay the utility for. kW is the useful portion of the beer, and that's what you want to use. And we need to reduce the amount of foam that's on the top, the kVr. You have to pay for that. It's always part of the deal. It's a matter of your load, but if you can reduce it, you increase the amount of usable, you decrease the amount of kVA that you're paying for and not getting anything out of. So, how do we do that? Well, I said that inductive loads have a positive power factor. That means our S triangle, our power triangle, goes up. A capacitive load has a negative power factor. That means that it swings towards the S becomes a negative vector. Well, most industry have resistive and inductive loads. A motor, a transformer, these things are inductive. So how do we correct an excessively inductive load? Well, if we have too much positive 90 degrees, we add an equal amount of negative 90 degrees and we can create it to 0. We'll never get there, and we'll discuss that reasons why we don't actually want to get all the way down there. But essentially, inductors and capacitors cancel each other out. So if you have 10 ohms of an inductive load and 10 ohms of a capacitive load, you add them together and you add up to a 0 power S and purely power resistive load. Here's a picture of pole mounted capacitor bank. Notice there's 3 boxes up there, 3-phase. They are expressed in kVAR and not farads. Again, we discussed that in our first lecture. They are boxes, not cans. You can see can on the back right side. That would be a transformer. But the capacitors themselves are three-phase boxes there. So here's kind of a graphical representation of real and reactive load versus power factor. So if we have 1 VA of real power, okay, that's 1 watt of real power with no reactive load, you have 1 VA of S, and it's a 1-for-1. If you end up with 1.03 VA, you have 0.23 reactive power. And it goes all the way up to, if we end up with 2 VA, you end up with 1.73 Q. It increases, but you never get any more power out of the system that's usable of 1 watt. So, other than the fact that you're paying for energy that you're not going to get any useful work out of, the utility company actually has penalties on customers who have low power factors. The increased current on your system is also respected on their system. So if they have too much load going to you and it's not useful load, there's just too much draw happening. Customers will generally look at the cost of the correction equipment versus the penalties, however, because the capacitors that you would add to your factory to repair your power factor comes out of your budget, not from the power company. It's on your side of the transformer. So you have to look at the cost of that correction device versus the penalty and use the appropriate economic decision. But here's something to look at and think of. A 9 kW load, 90 kW load. All right? If we have a power factor of 0.9, we end up needing a transformer of 100 kVA. If you have a 90 kW load with a power factor of 0.6, you end up needing to buy a transformer 1.5 times the same size of the 0.9 power factor, which means you have increased wire size because you have increased current potential. So if you, in this case, you can see where the capacitor would end up decreasing the size of the transformer and then decreasing the penalties required also across the board. So again, that's the power factor and means of correction. Resistors, perfect power factor, unity. Inductors have a lagging power factor. Capacitors have a leading power factor. Lagging power factor means that the power triangle has a positive angle. Leading power factor means the power triangle has a negative angle. Inductors and capacitors are 180 degrees out of phase from each other. Inductors are positive 90 and capacitors are negative 90. So when you add them together, you can cancel them out to increase or decrease your power factor to a point where it becomes 1 at unity. And most loads in industry are inductive. Thank you.